you. Apparently the recording is now in progress. There you go. And it's absolute pleasure to introduce Andy. And I have to say a big apology before I even do that, that sort of we're not all there. We should be all there, but we're on various interview panels that could not have been moved. So that was really just a very unfortunate coincidence that we're not all there. I'll try to be there for a little while and then I have to leave, which is very unfortunate. But so here goes. Andy has been a fantastic asset to IDSAI. He's joined us in September 2021 as a pure mathematician, is my understanding. And he's given us a lot of research capacity for computer vision and for, obviously, he's talking about neural networks now. His expertise is in computer vision and mathematical modeling for oceanographic optical transfer. And I don't know if that is what the talk will touch on, but certainly it will, of course, be about deep neural networks as dynamical systems, which is a great talk for all of us to follow. So I can't wait for it. So take it away, Andy. And thank you for being part of IDSAI for as long as you have. And we're really sad to see you lose to DigiLab, but in our heart of hearts, we kind of feel you might be back. Or we hope you will be back. But yeah, everybody enjoy the talk that Andy gives.
Okay. Thank you, Miriam. Yes, I am going to DigiLab, which is a startup company down at the Quay in a couple of weeks, but it's only at Exeter Quay. I'm not going that far away. You can probably still get hold of me. So yes, I know. So at IDSAI, we're all from different backgrounds. My background is originally in pure mathematics, where I was originally sort of taught that seminars like this are probably best broken down into three parts, where the first part is motivational and non-technical, second part more constructive and educational, so that we're all on the same page, and then the third part is where the really good stuff happens, where we start going into the details of the proofs and we start seeing all the mathematical tricks. And that usually works quite well, because by the time you get to part three, most of the audience will be asleep. But for those of you that do feel compelled to stay awake to the end, what I'd like to get to today is to understand or redefine deep neural networks themselves as solutions to systems of ordinary differential equations, so dynamical systems. And this is a big motivation in my research, but before we get there, I suppose we really need to think of a more fundamental question: what are deep neural networks themselves? So let's have a look. Let's go for a sort of Radio 4 documentary high-level thought about this. Deep neural networks we think of as being able to analyze complex information, and you can draw inference on this information, on this data, by making predictions by pushing them through black box simulators. But what are these simulators? Well, they're modeled on the human brain, how the human brain works. So that this information is traveling through synapses, activating neurons and sending the information elsewhere before it's returned, perhaps out your mouth. And kind of this is the overall structure of a deep neural network. Certain features of them, that these machines are highly parameterized. So I'm talking on the order of tens of millions of parameters, at which point all the statisticians start to look a bit queasy at that. They're also sort of, another defining feature is that they require a lot of training data, a significant amount of training data. And what do we mean by training? So we're talking about optimization. We have training data can consist of things like images and labels, or translations, or some sort of target to teach the machine. We pass that through the deep neural network modeled on the brain to get a test prediction. We then look at the prediction. Is it correct, we ask ourselves, or is it conforming to some sort of reinforcement penalty? Then we send it off to some sort of high performance computer to compute, crunch a load of gradients, make updates to these parameters, and we start again. And this training routine can take a long, long time. However, one thing that sort of, as a researcher, I struggle with is that whilst there's a lot of research going into architectures of neural networks and how they perform, there's very little updates or changes that have been made to the optimization routine itself, so updating these gradients. So that's one thing that I'd like to really think about in this talk. Another defining feature of neural networks is probably sort of unsuccessfully, they're not very interpretable. In fact, not interpretable at all, let's say, compared to other types of modeling techniques. So this is something else that I'd like to try and unpack in this talk. So before we get bogged down in the sort of theory of deep neural networks, let's just check where we're talking about something meaningful. Let's ask ourselves, why do we need deep neural networks? And I should also say, when I'm talking about deep neural networks, I'm really thinking about the depth aspect itself. So what sort of models and what sort of applications require deep networks as opposed to other modeling techniques? So in which case the deep neural network is state of the art, and in which case are they the only tool that we have to solve a problem? So let's look at some examples. So in industry, self-driving cars are essentially governed by deep neural networks, processing images. They take cameras on the side. Algorithmic trading, I suppose people in stock markets have realized that if they get neural networks to make predictions a lot faster than humans standing there saying buy, buy, sell, sell, sell. Demand forecasting or nowcasting is a technique using sort of GANs to be able to predict sort of very quick weather forecasting scenarios. In healthcare, neural networks have sort of changed the way we think about drug discovery, or in terms of that they can search a very wide parameter space and make predictions on which drugs are going to be successful. The spread of disease, so forecasting in a time series sense, boosting MRI diagnoses, or even any sort of image-based clinical diagnoses. You often see in the news that there's been some deep algorithm that's predicted a certain disease much better than doctors themselves. So this is not just beating models now, but it's beating clinical professionals. And one example of this is when we look at making diagnoses from MRI scans. Some people have introduced a sort of back propagation method where we can use those diagnosis predictions, but given that neural networks aren't very explainable, we can start to back propagate the signal or the diagnosis to light up areas in the MRI scan which are significantly impacting the diagnosis. That's a very interesting piece of research. Where are we? So technology, and I'm sort of thinking about resale technology. So this is occurring in things in your devices, speech recognition. If you have some headphones which do background subtraction or noise cancellation, these will be using deep neural networks. Image enhancement is sort of very popular as a selling point in devices. So this is my sort of favorite party trick at the moment. If anyone has a mobile phone which happens to be the type which begins with I, then the last update included deep neural network in their Photos app. So specifically what happens here, you can take up a photo of your favorite family member. Let's not share this with my wife, please. Get your finger and just put it on the object, and immediately the iOS will implement a deep neural network background subtractor, and you can just remove that family member from the background. And then by the time you're that far, you can give us new toys, maybe take her on a day out, and send photographic evidence to the grandparents. So, I mean, well, you have to have something to do at 3 o'clock in the morning. But that's a deep neural network literally at your fingertips. Which something else I quite find fun is mathematics. So here you find deep neural networks in time series forecasting, in modeling solutions to ODEs when you just have sort of test data, and even matrix multiplication. So here the scientists at Google Brain have developed a deep reinforcement learning algorithm, which is been systematically taking out grand masters at chess, more recently world champions at Go. But in a piece of research called Alpha Tensor, they have managed to codify matrix multiplication into a game, and they use their reinforcement learning algorithm to solve this in such a way that it beats all current numerical algorithms, the best of which has been sort of a long-standing algorithm in the past 60 years. So it's very impressive, almost covering when matrix multiplication in computation has been important. So I dare say this sort of algorithm will be turning up in your, I don't know, in scikit-learn or MATLAB very soon. What else have we got? Language processing. Natural language processing is sort of the study of how we communicate and codifying that into deep neural networks. So this is very useful when you look at election campaigning. It's very useful when research going into cognitive diagnoses from speech and even translation. So for example, Google Translate, this is powering a lot of the translations, interpreting what you mean into what they might be translated into in sentence-wise patterns. And even on Google Translate, you can input videos of text, and a neural network will be performing text recognition, first of all, which sort of leads us into our next category of computer vision, which is probably the most successful category where deep neural networks in particular have been applied. So some examples are self-driving cars, which I have already come across, so that's probably a typo. So let's change it to, for instance, number plate recognition. A lot of car parks these days don't require you to take a ticket because they're shining a camera on you, and that camera will have a deep neural network in it, recognizing your number plate. There's some research proposed to look at CO2 auditing of buildings by looking at map data from a computer vision perspective, and visual recognition. So probably the strongest still, this kind of algorithm is very sort of well, okay, let me start again on that one. So visual recognition, we're talking about object detection and classification. And now you can get these sort of algorithms off the shelf and just use it in your own research. And that looks something like this. So it sort of changes the field of remote sensing to one which you can start making predictions and data collecting on a much vaster scale than beforehand. So to give an example of this, I'm going to quickly jump to a topic which I like very much, the IDSAI CCORN projects. And so I'm sure most of you know that IDSAI is a collaborative, cross-disciplinary network of research academics. All right, Helen. Okay, good. But the other thing that IDSAI has attached to it are offering these CCORN projects, which are 6-month-long projects where you can win a postdoc, an AI postdoc, to work on your data science or research idea. Unfortunately, the deadline for the most recent call was literally yesterday. So that gives you sort of 6 months to start thinking of a new proposal for 6 months. The last project that I worked on was called VESP AI. So this is with Julia Osborne's team down in the Penryn campus, and their problem, well, I suppose all of our problem, was that of the invasive insect species Vespa velutina, also known as the Asian hornet. And they wanted to develop an AI device to monitor and detect this hornet, which is becoming more and more prevalent in the UK. Their idea, which they submitted to IDSAI and got funding for, was to build a bespoke bait station, which would have an AI detector in a camera built into a Raspberry Pi on top. So this way they could collect, monitor, and hopefully stop the spread of these hornets. And the long story short is that, well, we managed to train a very successful detector. It could perform well on target detection, finding the Vespa velutinas themselves. It could separate Vespa velutina from Vespa crabro, which is the sort of incumbent native hornet species, the European hornet. We were able to separate from bycatch and swarms of hornets which were coming in. But the point is, training this kind of model, we didn't really unpack or unpick the nuts and bolts of the deep learning architecture. So here it's more about experiments, choosing the data correctly, feeding it into the machine in a certain way, augmenting it, changing the rhythm with which it's learning. But the nuts and bolts sort of remain the same of object detection. However, that's the part of deep neural networks which interests me most from a mathematical perspective. So at a first glance, one method that we could have applied was something similar to the MRI detections, where we can apply a heat map back propagated from the classification decision back to the original image, which shows relevance of each pixel dependent on the classification decision that was made. So when we apply this across the board, we get some sort of projection about the relevant features in the image, which are making a classification decision. However, this isn't really showing us why something is, say, a European hornet or an Asian hornet. It's just sort of lighting up some areas. If anything, you can just use it for checking that you haven't made any mistakes. Say the machine isn't detecting a timestamp on the image, for instance. And so this gives us a new pipeline for explanations where we feed an image into a deep neural network, we obtain a successful detection, then we put that back into essentially another deep neural network to gain some sort of explanation. However, this is just a projection, and really we still haven't touched on what's going on inside. Well, that's fine, because that sort of neatly brings us to the main question of the talk and the start of the talk, when we're going to start unpacking that box itself. So today I'm going to talk about, first of all, that was the motivation part of my three-part monologue. Part two is going to be the educational part. So we're going to talk about constructing deep neural networks, and we're going to particularly focus on the role of depth in this. And then we're going to look at what happens when you start adding more and more layers. And this is what you really need to do in practice when you're applying these models. And in particular, what happens when we take the limit to start looking at infinitely many layers? What does this lead to? This leads to a description of neural networks as continuous dynamical systems. And when we get there, then we're going to talk about some current results in this field, and some open questions and just sort of things that I've found interesting and motivating over the past year in this topic. So I think the best place to start is right at the beginning with our favorite linear model. So let's talk about what's going on in a linear model. Well, we've got inputs, and we're going to think of these as a vector x. I'll probably refer to the components as features. And for each feature, we introduce a parameter, a scalar value, which we then multiply to the feature and sum up to give some sort of predictor in our training regime. That's fine. And linear models, they're very simple and often not applicable. They can't describe what really happens in reality, but they should be sniffed at because they're sort of the ultimate interpretable network, as these parameters, these W's, give a scale of how relevant each feature is to your problem. But okay, so let's take a short step into something slightly nonlinear. Let's look at a logistic regression. So in this case, we're going to put a sigmoid function or a logistic function, which is here, on the output of our linear model. And then this can be used for problems where we want to maybe classify two things given a continuous variable. Maybe you want to plot the answer to the question, do you believe in Santa, as a function of age? Whereas if we took, well, maybe that's not a good example. I suppose I'm still down as a maybe. And I guess this is the kind of maybe region. You'd hope that would follow a sigmoid logistic function. So that's fine for that sort of thing, but it's still very restrictive because you're still just thinking of that kind of data structure. So what could we do to make this more applicable? Well, we could think of lots of these sigmoid outputs. So here, what we've done is taken our vector inputs and then applied a logistic regression lots of times. And that's what's happening in this red column. And now what we call this is a perceptron model. And as we've stacked up lots of layers of these logistic regressions, we call this the width of the perceptron. So we haven't got to depth yet, but now we can think of wide networks. And the reason that these are interesting is because in the limit, or as the width becomes arbitrarily large, predictors from these neurons are universally approximable. So that is that you can predict any continuous value function from R to R, and this can then be extended sort of vector-wise. So really you have a good understanding of reality. But as you can see, we're starting to lose interpretability because this is already a bit of a mess. I'm calling these logistic regressions now neurons. And that's because this, as you saw, the sigmoid function was sort of indicating whether something was going to be 1 or 0. And we think of that as a sort of activation which is occurring in the brain. So what's the natural thing to do then if we've started writing down wide networks? Well, let's write them down deeply. So let's start connecting all of those logistic regressions now to further logistic regressions and stack the inputs from the outputs from one layer into inputs to another. And then we have the sort of most basic stereotypical deep neural network. We'll call this a multi-layer perceptron or a fully connected network. And as you can see, the parameters required. So from one layer to the next, we had a matrix of parameters. We now have multiple matrices of parameters given how many layers we've got. So now training these things becomes very expensive. These networks at first sight, okay, so I was also going to mention that this is the sort of most vanilla type of neural network. When you're looking at image analysis or other types of problems, you have different techniques. You can put convolutional layers, which I'm not going to talk too much about, or you can apply techniques such as batch normalization, use Monte Carlo dropout to run your network to improve performance. Not necessarily give explainability. I suppose some of them do, and we can talk about that later. But they're more, in practice, there's a much more technical sort of explanation of this. So the real question is, how do we train them? And let's just go through this quickly. So we want to pass an input through our neural network. We get to the output, we want to compute some sort of loss dependent on a target. And then we want to backpropagate this through the network. And this is done by an explicit formula given by the chain rule. And this is something that hasn't really changed in terms of introducing different architectures. You can have much more complicated architectures, but we still want to compute losses with respect to the parameters themselves via the chain rule. So let's look at what this means. This means that this rule here is a sort of very basic mathematical formula which says that the derivative at one layer, say this layer in the middle, is entirely dependent on the layer beforehand. Sorry, the other way around. So iteratively, we can take a step back into the network and say that the layer L, say, is dependent, layer L plus 1 is dependent on layer L. And so the derivative of the two are related by this expression here. So this lets us compute parameters at each deep layer. However, in forward passing, you have to remember all the paths that you've taken, all of these blue lines, and store them in a very large tree, essentially, for then going backwards and backpropagating the error. So this is sort of one problem. They're very expensive in memory. Another problem is that gradients can vanish in this backpropagation routine. And what I mean by that is that for some sort of surreptitious reason, by the time you've taken the gradient up to this layer, well, you might, for some reason, have a vanishing component of this formula, and all of the gradients downstream are then going to be 0, and there won't be any effect of the network there. There won't be any way to train those parameters. So let's look at a remedy for this. Remedy for this, which has been very successful, is called residual learning. These are abbreviated to ResNet. And for residual learning, we make another slight change in our neurons, where instead of letting the neurons be some collection of logistic regressions, we take a copy of the layer before and we add it to the next layer. So this is called a skip connection. We take an identity copy of the previous layer, add it to the next one, and then add on the function that we're trying to learn, built from these parameters. How does this solve our problem? Well, when we start differentiating layer L plus 1 with respect to layer L, then we immediately pick up a copy of the identity component. And so that even if the training function starts to vanish later down the line, then the identity propagates backwards and can pick up the parameters sort of downstream. So this is a type of network which came in 2016, and it's become state of the art. It's allowed people to build incredibly deep networks, sort of up to 100 layers deep, while still being able to backpropagate through them. And it sort of has won lots of competitions. I mean, I dare say it's the network which is segmenting our children from our photos. And it's the main feature of all sort of deep learning techniques. But there's another feature of ResNet, which is sort of very interesting, because now that we've added on this skip connection, this identity term between layers, what we're really learning is the linear gradient between two layers, rather than learning the function itself, which is what we were doing in the multi-layer perceptron case. So to say this again, with a ResNet, we're taking an identity, a copy of the identity from the layer before, and we're adding on a function that we're trying to train. Instead of doing this, we can realize that expression as taking the Taylor expansion between the two layers and chopping off all of the second order terms as a function of the distance between the layers. In the ResNet case, that distance is 1 because we're just taking small discrete steps, but we could generalize that distance to be a distance epsilon, and epsilon could then become arbitrarily small. So in this way, we can stop taking discrete layer steps and move to continuous layer steps. And then our model, in analogy with the ResNet idea, it would be to model the dynamics of this continuous function. So what's the model going to look like? We'll now model a deep neural network as an initial value problem. We've still got inputs. This is our input vector X. And we come across another black box. We put these inputs into an ODE solver for some arbitrary training function. So the training function will be the dynamics function. It's written down here, which we'll call F, and we'll let it be parameterized by W, a set of weights. And then this will give us outputs according to now not a depth of a network, but some continuous interval. What does this sort of mean, I don't know, philosophically? It means that what we've done is started to consider a continuum of layers and perhaps even infinitely many layers. They only become realized when you move through the ODE solver. However, the ODE solver can be chosen to be an adaptive one, and it's sort of decoupled from the sense of needing to actually evaluate at a given layer, so you can take larger steps over a few layers if they're irrelevant, while still simulating this dynamical system. So that's the new model that we're going to see. So that's the kind of comparison. We're moving from deep neural networks into modeling dynamical systems parameterized by some weight parameter. So the weight parameter, beforehand, we had weights. We had a matrix of weights at every single layer, L. Now we're going to have a matrix of weights at every time t. And this starts to introduce the problem of, well, beforehand we had L layers. Now if we've got infinitely many conceivable layers, how do you parameterize that function? So this is a very interesting and open question in understanding these networks. So here's our network, and these are called, these have been coined as neural ODEs by Chen and his collaborators in 2018. The sort of picture to understand them is that when we were looking at ResNet learning, we were taking discrete steps through the depth to build up a picture of a vector field, whereas in an ODE network, well, we can now just take adaptive steps at different positions, and we're not bound to a constrained amount of layers, and we get a better understanding and a quicker understanding of the vector field. Now, I suppose the main question here is, how do we update these parameters? Can we still do backpropagation in the same way? And this is a sort of really quite nice feature of their work, is that they realize not only can you use backpropagation, you can kind of derive a much more interesting formula, but still using the same chain rule idea. So what do we do when we backpropagate? We're looking to a loss, and we want to differentiate the loss with respect to, first of all, the endpoint, so the final layer, but really we'll want to differentiate the loss with respect to every single parameter. So this sort of is equivalent to being able to push this function here, this loss derivative, back to the beginning of the network. And how do we do that? Well, what Chen derives is a formula, another differential equation describing this loss gradient as an adjoint flow. So that's what's replacing backpropagation. And let me explain some implications of this. So first of all, to prove this, so the thing that is really quite beautiful is that you can prove this almost explicitly with the chain rule, sort of substituting, taking an infinitesimal step of size epsilon as we send sort of epsilon to 0, and looking at how the gradient changes across that boundary and plugging this into the definition of a derivative, you can derive this formula. It's not the only way to derive that formula, and I'll say some more about that in a second. But in doing so, they sort of give this, in deriving this formula, this is not something that we could have done with the discrete network. And what it does is decouple the backpropagation process from the forward pass. So what I mean by that is that when you want to train your network, you forward pass through this black box ODE solver. You gain your prediction, which is your network state at the endpoint L. And then that's all you need to backward pass, because you've got this explicit differential equation to solve in return. And where was the obstacle beforehand? Well, beforehand, when we had a discrete network, we were saving each step of the function computation and building up a gradient tree. And this is how you normally backpropagate. But in this case, we can decouple the two, essentially meaning that you can backpropagate with bounded memory, rather not with memory that sort of grows in proportion to the depth of the network. So that's a success. That's great. That's kind of the result of this paper, that you can backpropagate with bounded memory cost. But the main limitation is that the parameters that you're trying to optimize are fixed to be constant throughout the entire network. Okay, so what does this mean? If you think about at the deep neural networks we had on earlier, it's like saying that the parameters at every single layer are exactly the same. So you're not really allowing any parameter variation to change the state. It's only the state itself which is allowed to vary continuously between them. So when you're trying to make the, I don't know, the fancy argument that, oh, we've got an infinite depth neural network now, it's sort of more like a one-layer neural network with a very sophisticated sort of forward pass. However, this does then bring in some interesting research into how can we let this parameter vary continuously as a function of t. Well, let's talk more about that. So as with residual neural networks, kind of gave us this theoretical understanding of how training functions can be considered as dynamics functions, essentially. This paper gives us an understanding of neural network optimization as a two-point boundary value problem. So what do I mean by that? I mean that we have a forward pass letting us obtain an output, and then a backward pass letting us obtain a loss gradient for which we can update the parameters, which is completely described by this two-point boundary value problem system. So we should be asking ourselves, how do we solve such a system? And by the way, this is a sort of constrained system in that we're trying to minimize the loss, of course. So now we're going to take a step back. So it wasn't originally computer scientists that had these ideas. In fact, this goes all the way back to Euler and Lagrange in the 16th century, I believe. This is a sort of classic PhD student supervisor relationship. And what Lagrange had the insight to do was, well, maybe he didn't have this insight. So first of all, he thought, where Z of t here is our network state propagating through the system, let's consider small perturbations around that network state. So this is sort of what you might do in, I don't know, sensitivity analysis if you're trying to optimize the system just by making small perturbations in your parameters, what happens to the output. So he's making small perturbations into the state itself, and likewise into the, which has implications for the parameters too. And then we compute, so to find the optimal solution to these parameters, we compute the Gasso, which, as we've just taken a small step epsilon away from the optimal trajectory, differentiate this, the loss with this expression in with at epsilon equal to 0, and set that term to 0. I mean, it's optimization. Ultimately, all you do in optimization, you're trying to differentiate something and set it to 0. But this is sort of a bit more subtle in the sense that we've done this in a continuous way. It's happening for every t, which gives us a continuous integral constraint. And lo and behold, if we use this method, we can prove the adjoint formula that Chen derives using the chain rule in a slightly different way. But it comes out, you use some sort of tricks, integration by parts, very nice. But another thing comes out which isn't picked up by Chen, and that is that you have an additional optimality constraint fixed for every single t along the network. Okay, so this now has sort of rephrased the ordering of the logic and how we see this problem. We're not now forward passing and training. We're saying from the outset, I'm going to assume I've got the optimal solution. And that's what's happening when I impose this condition and then I just unfold. Well, so, okay, so if I have an optimal solution, then this is a first order condition. That's fine. Let's just assume that's the same thing for now. And in that case, then this system must be satisfied. This system must be satisfied. And in addition, this optimality constraint. So this optimality constraint, in fact, when you work through the equations and you take this case when W is not allowed to change with respect to T, so it's a constant throughout the system, it sort of pops out at the end of your backpropagation integral, and that's how you make your update. So it is still happening behind the scenes. However, for us, it would be nice to just be able to solve this whole system at face value, because then we have an optimal system. That's a difficult thing to do, mainly because of the coupling of these differential equations. So we forward pass, we obtain the output, and then we backward pass, we obtain the loss. So let's say we wanted to make okay, hang on, I think I'm going to look at this in an example on the next slide. It might be slightly more clear, right? So here's an example. Let's consider the network. So that is the state derived, controlled by a dynamical system, dz to t equals f, where at f is equal to a matrix multiple of the sigmoid function that we saw before of our network state. So this is a direct analogy to the multi-layer perceptron that we had beforehand. In fact, it's just a continuous extension of it. The only difference is that W is on the outside rather than the inside. But if you sort of think about it in a continuous way, we're applying sigma to Z just in the layer before in this setting. And as we've sort of taken the continuous limit, this is constantly happening. So every time you evaluate it. So it's as if the W's are coming from the layer before, but that's fine. It just makes it easier to differentiate when I want to write down a formula. We'll do one other slight quirk. We'll include a quadratic penalty, which is actually something you commonly do in your network optimization on the W's. So we want to minimize this for all T, this expression here, where Q is the quadratic form. And running through the equations and explicitly computing the optimality constraint, we can work out an explicit formula for the W's. So maybe the goal's complete. Maybe what we've done is we've had a new definition that we can work through, and now we've got an explicit form for our parameters. We don't need to do any training. Fantastic. But not quite fantastic, because we are still considering a 2-point boundary value problem. If we want to compute Z of t, we have to solve this equation. So we need W of t. So I'm sort of saying, well, let's plug W of t in here. But for that to happen, we also need to know lambda of t. And lambda of t is only obtained by finding Z of t at the end of the network and then back propagating. So we've got a conundrum that we need to solve. How can we find an explicit solution to lambda, which is our adjoint, or if you, in another sense, it's the gradient of the loss being back propagated through the system. And so far, there's sort of been 2 attempts at this. Number 1 is with something called the shooting method, or the particle shooting method, by Lard and his collaborators. In this method, you're essentially looking at your 2-point boundary value problem, and whereas you have an initial you have an initial condition for Z of t, the network state, you don't know what the initial condition for lambda. should be, you're a joint, so you take a guess. And you do this multiple times for multiple particles, so you're just sort of shooting particles down this differential equation. I suppose it's more like sort of shooting in the dark, and then you see where they end up at the end of the network, and you sort of take the closest one to what should be the actual value. So what am I saying here? I'm saying we've got an arrow pointing in one direction, an arrow pointing in the reverse direction, and instead we turn around the bottom arrow by just taking a guess at the initial. And it's a very interesting method and a very successful method as well. And it sort of gives us, with this kind of formula, it gives us a very, well, a much more interpretable way of understanding the form of the waves, given a quadratic penalty, say, or given the structure of the network, because we had to explicitly differentiate this and write this down, and that's the form of the parameters. Helen's giving me the thumbs up to keep on moving. Oh no, she's giving me, oh, you're enjoying it. Even better. Oh, right. Get up. Anyway, second method is one that I was working on with my collaborator, Dimitri Kangin, called the invariant embedding method. So let's look at this solution method for the same problem. This is where things start to get a bit meta. So in our work, we tried to explicate the dependence of, well, I'm going to say network depth, but I'm thinking of the network depth by fixing the endpoint, and then I'm going to vary the input location. So this set of t here is now going to be the set of t, which is x input into it at position p. And so you're sort of stretching and moving that network. And then we embed all these functions into a family parameterized by p. So where p is the length of the network or the position of the initial condition. And what we do is we explicitly derive a partial differential equation, which is letting us write down how this z here changes. So explicitly in x as a with respect to p as an explicit variable in terms of the change that has to happen in the initial condition. This gives us a new network that we can then integrate. So we're changing variables from t to p, and when we do this in practice, we fix t to be the endpoint q, and then we integrate backwards with p. So here's what's going on. We've embedded one system here. So this is z of p and p of x, because we've introduced x at t equals p, and then we've got another system in the family which we introduced at t equals p plus epsilon. But they all must obey the same dynamical system. And a similar situation for the backpropagation formula, the adjoint method. But let me just sort of try and explain. It's a bit of a strange idea, so let's explain it in another way. So let's go back to thinking about feed-forward networks, hidden states. We have inputs and we want to push them forward through different layers of our network. So calling on the discrete analogy again, to gain our output, and our depth is measured by those layers. So in our networks, the invariant embedding networks, we consider the model as starting from the bottom here, and we're modeling the output of the network. So at every step in our depth, we get us, if you like, a valid network output. So our increase in depth is sort of moving up as we've stacked this family of networks into each other. And it sort of sounds like we're getting something for free. I can see you sort of looking a bit skeptical about this, and we're getting a network for every single depth, but this is theoretical, because in any case, these networks need to be trained. So we need to decide at which point is the output going to be relevant to our predictive model. So fine, but before we start thinking of the feed forward problems, let's just have another think about what this means in a predictive, if we want to consider a regression problem this is a graph for projectile motion, where we've got position along the x-axis and height along the y-axis, then we might take some points along this red curve here and use those as our training points for our network to simulate as depth is in parallel position. In our invariant embedding networks, what we can use is the height and position of a projectile that started at multiple different locations, but we just take the end recording as our sort of continuous variable, because we've switched variables from t, which is this axis here, to p, which is the location of the input. So that's the sort of difference in terms of a time series problem. But for me, it's more interesting to consider sort of feed-forward networks, because that's sort of where the mystery of depth is really happening. And one example of this is looking at a problem where we want to rotate MNIST digits. So here's an example of the digit 3. So in this experiment, we have, well, the ground truth on the top line here. And in the second line, at p equals 0, this is sort of depth 0. So if you like, our embedded network is trivial. The input is the output. And we want to predict how this, we start at the middle value because we want to look at rotations left and right, how this 3 rotates into, so what we do here is we evolve the number through layer on layer on layer. And as an example, we decided to train at layer 4. So this is what we hope is the most successful layer in it, and it is, because that's where we were taking the loss with respect to. But then with these networks, as we're giving outputs at every single depth, suddenly we can see what happens deep into a network, because well, the output is meaningful suddenly, not just a sort of deep hidden state. So when we've got the trivial network where you probably expect that no rotation happened at all, let's bring up the loss of this function. And so plotted in different colors are the different depths here. And one interesting feature about this plot, so we've got frame ID along the bottom, is that rotations prefer to either be extrapolated or interpolated when you're moving along the sort of depth axis. So if we've trained at layer 4 here, or sort of thinking is the output layer is 0, moving backwards in negative numbers, sorry about that, then when we start moving to layer 5, 6, 7, and 8, well, then we've extrapolated beyond the depth that we had originally. And of course, as we start moving up to depth 8, we start getting much worse loss in our system. But it's already an interesting observation that these things are asymmetric. Okay, so that was one solution to that boundary problem. Another interesting thing about these deep neural networks, these continuous neural networks, is that they require, they are evolutions of feature space. They are evolutions of feature spaces. So what we first have to do is pre-process the data to go into them. And this is done manually in practice. So we were trying to think of a way to include this into the deep network, and we looked at the kernel trick. So what does the kernel trick tell us? Well, if you have an input space X, you can apply an abstract feature map by moving into some high-dimensional Hilbert space, and then you project down back into your target space by taking the Hilbert inner product, and then the kernel trick is to essentially say every time that you essentially get X transpose of your data, every time you get a correlation matrix of your data, then you apply a kernel instead. And this features in lots of different solutions. For example, just the solution to ridge regression, or in support vector machines, or indeed in Gaussian processes. And so in this way, you can extract features from your data set without ever having to write them down, because the kernel contains all the information of the projection back to the target space. So our adaptation of this method was to, let's think about what happens in a neural ODE setting. In a neural ODE setting, we apply this feature map by hand, we have to compute it, then we propagate and evolve the features according to some dynamical system, and then we project back down onto the target space using the inner product. So what we introduced was the kernel ODE trick, if you like, which is where we can write down kernels dependent on dynamics of some dynamics function, and this is where the trick comes in, and skip this top high dimensional processing layer completely and just apply these new evolution parameters to the kernel method itself. So what does that mean? Let's try and think about that. So here's a nice slide with lots of maps on. So our kernel trick is to write down, we'll take a kernel to start with, and then we'll say that the output of this has to satisfy some differential equation. And then the conditions for which that the final kernel is still a kernel are essentially given by a list of equations, but more or less, you just have to take the dynamics function to be a kernel itself. So this means we can do things such as adaptive kernel selection. For instance, we take our dynamics function to depend on the previous kernel multiplied by some parameters, which we're going to learn. And perhaps these parameters start vanishing if one kernel is not performing well. So we can combine lots of kernels and see which one works better. One example of this in a sort of basic setting is here we're just trying to predict the ground truth function, which is given in a blue dashed line. You can see it better on this graph, with our green prediction. And we complete this regression task based on the red data points. And on the left-hand side, we're just using a normal Gaussian kernel method. On the right-hand side, we're evolving our Gaussian kernel, mixing it with a linear kernel. And this gives us a sort of evolution of the kernel as, again, we get a valid output for each depth step in our kernel ODE. So the graph that you see in time is moving in time parallel to depth. And what you could interpret this as being, so if you were to train this iteratively with gradient methods, you would expect that your solution would start to converge to the actual solution. But this is a final finished model. So this is just how the model's working as a function of depth. There's no more training, there's no training going on behind the scenes here. Right, Helen is really giving me the eye now, so I'm going to start speeding up a bit. So we'll have some coffee later and there'll be time for more questions, but I might just fly through the last slides to say other things that have been studied are trying to parameterize the weight matrices in neural ODEs, first parametrically with these kind of explicit formulae, then by things such as hypernetworks, sort of maybe building a hierarchical network and abstracting the weights to another neural network, which gives you outputs for every depth layer, which is method. Google Brain looked at a way of constraining the weights to the orthogonal group and modeling them by an ODE. And a new work that started working on with George is to understand how these weights evolve as a Gaussian process. So how the depth can be used as the sort of input to a Gaussian process prior. And then, of course, we have some difficulty in using the posterior because we've got a highly nonlinear system. So this requires making a map estimate. In fact, we use Laplace approximation, requiring a new theorem about the Hessian of a neural ODE. But this kind of opens the door for more gradient-based methods, perhaps Newton methods involving the Hessian. And let me just sort of, I've faded them out so we can't just look at them. So then I just wanted to say that I've got some ongoing projects which would be welcome to talk to people about. And I'm going to do them anyway. I'm going over time, I suppose, but I'm going to talk about them anyway. So when we're talking about embedding neural networks, quite a cool feature is that you could, or in fact you can, extend your network state to include the depth axis, or rather the t-axis itself. So this means you can compute gradients with respect to t and start to optimize the start and end points of your continuous neural network. With the invariant embedding approach, and you can actually write this down as a function of t and solve explicitly a form for the locations of the depth parameters in terms of the function that you've introduced itself. So this is quite a fun thing that can be worked on. This idea, Bayesian kernel ODEs. So you sort of saw that regression approach happening. I think it might be interesting to apply this idea with Gaussian processes using these kernel ODEs as the kernel function and see how uncertainty evolves as a function of depth. There's some work with optimal echo state networks, so looking at reservoir computing from a dynamical systems or from a continuous perspective with this idea of the Euler-Lagrange method. Using the Hessian result for networks. And the trick here is that we can do it with bounded memory, just as Chen was able to backpropagate with bounded memory. Use Newton methods to optimize deep neural networks. Yeah, thank you very much.
Well, thank you very much, Andy. That's really fascinating. I've actually done something today. That's great. So yes, so I think I'd like to open, if anyone's got any questions, I'd like to open it up to the floor before we go on to the chat. So feel free to fire away if anyone's got anyone. Hi, George.
In your MNIST digit predictions, you showed that as you got deeper, or undeeper, whichever way around,
Undeeper, yeah.
Undeeper, you got to a point where it could successfully get the correct predictions, essentially, rotating the images. And then as you went more undeep, it got worse again. Did you look at going even further? I'm curious as to whether it becomes cyclical in terms of just getting deeper. Does it get better again? Does it get worse again? Sort of relates to one of your future works in terms of,
Yeah, in terms of finding an optimal formula. Yeah. So here's the graph. Yeah. So George is asking about for the microphone. In this graph, we trained the network up to level 4. And his question is, this is getting worse as we get undeep. So as we move up towards level 8, is there a point where it starts to get better? So the answer to that computationally was that the loss was so great that we couldn't be training the neural network. That was the problem, but that's a very interesting idea. So if we tested this on something simpler, I don't know, just trying to predict points around a circle or something, then I expect the loss would be constrained, and it would be interesting to match kind of that sort of experimental idea with the idea of optimizing with respect to depth in theory. But yeah, we didn't observe that experimentally.
Anyone else got another question? Have a look at the okay. So is there any published reference on the kernel ODE work?
That will be coming out soon, and it'll be on archive soon. Not yet published.
Right. Okay. And David's asked any recommended sources to look at on your primary example, on your preliminary examples in more detail.
Yeah. So I think you might even be able to get from the video of this talk the details about the MRI paper in particular, but I can send it some more interesting reading sort of examples.
Well, thanks ever so much again. I'd also like to thank Miriam, who steps in just to introduce Andy. She's our interim co-director in IDSAI, probably all met before. Arrange tea and coffee. Hopefully it's just outside waiting for us. Just a plug from me. Our research seminar series continues, so keep an eye on our website. If you're on our mailing list, that's brilliant. If you'd like to be on our mailing list, if you're not on our mailing list, then just email IDSAI at one more plug from me. If you fancy joining our IDSAI ECR network, then again, drop me a line at IDSAI. We're looking to create a community of like-minded scientists interested in data science and AI. great to have you on board. So that's all from me. Thanks again, Andy. Yeah, tea and coffee outside.